today in this what promises to be really an enlightening discussion on one of the most innovative topics at the moment in the energy segment. And with me here today, I have Mr. Miyanaga, if I'm pronouncing it correctly, Chairman of the Board in Mitsubishi Heavy Industry, Mr. Cosmin, Chief Executive Officer for Nuclear Electrica Romania, Miss Kristen Kogan, Founding Director and Co-Executive Officer at Terra Praxis, and Mr. Khan, these difficult surnames. Kefarian. Okay, co-founder, Kefarian, co-founder, chairman of the board of X Energy, co-founder and executive chairman of Axion Space USA. Thank you. So with that, I'll start the questions because there's so many interesting discussions tackling the nuclear energy. So, Mr. Miyanaga, yes. I will start with you. Following the recent COP28 and the recent International Atomic Energy Agency Nuclear Summit, yes. We see a lot of momentum building around the new nuclear. Yes. However, public perception is still dominated by concerns around waste management and environmental issues. Yes. According to you, what are the main benefits of the new nuclear and that can be led to a nuclear renaissance?
Yes, I'd like to say, the benefits of the nuclear power plant, or nuclear power, was a kind of the common knowledge it used to be. And then the somewhat, because of certain reasons and some accidents, recently the Fukushima Daiichi power plant, and then I think some such kind of benefits were forgotten by some people. And I would like to stress again those the benefits, very significant benefits of the nuclear power. Even in we have been enjoying over very long period the compactness with the conventional nuclear power plant, the very compact of the site size. And also not only the compact site size, but also the very compact and fuel availability. And then I think it is a kind of closed circuit for 1 or 2 year operation. And then if we decided to further explore such kind of opportunity, we can extend that kind of closed circuit operation. So, and that is one, and size and the long time operation, continued operation. And another thing is the very stable, power generation level. And with the progress of the technology and the improvement, now we can, adjust the power level to some wider range. It used to be at the 10% also. Now the 20 to 30 to 40% range is possible. And it is a very convenient, it has become a very convenient power plant. And another thing is a very, very stable and reliable power generation. On top of these things, we are developing another, or the other new benefits, like the much more stable, and safer, design and installation of the as a transition technology, immediate transition technology for replacement, the most advanced, next generation, large-sized and middle-sized nuclear power plant, and then the many people and organizations are pursuing to realize as soon as possible the small modular reactor, and which will have many, other kind of benefits, like the distributed, application is possible, and also if we integrate the small modular reactors, the sizing becomes big. And with some small application, it is very convenient for the local application for data center and others, and so on. And another benefit, if we proceed to, and MHI, our company, has been very active to develop the high temperature gas reactor, and which will be a hope for the very cheap, inexpensive hydrogen production with its very big high temperature capacity. And another one is a fast reactor to realize the recycling of the fuel and extended life of use of the wasted fuel, so and so on. And I hope in my life, and I would like to see the commercialized nuclear fusion.
Thank you.
Yes, okay.
Yeah, I was sitting beside Christy before coming out, and we were exactly discussing how this perception needs to be changed and brought to the mainstream. So from TerraPraxis perspective that I've been following, that's a lot of things that are happening. Could you share a bit of this perception and how this has changed and things that you've been achieving within the nuclear space and small reactors?
Oh, thanks. Well, I'm not sure how much we can take credit for, but it's absolutely clear that public perception, is now in majority of support for nuclear energy. There was a major survey that was done last year of several countries, including Sweden and Finland and Poland and the UK and Japan and Germany. And in every single one of those countries, they found a majority of support for nuclear energy. Now, that is because of the contribution that nuclear energy is already making to support energy security, energy price stability, and particularly in light of the experiences that we've all had over the last couple of years with very high prices and serious insecurity in our energy supplies. But there's also additional benefits that people are really beginning to recognize, particularly in the context of, frankly, the abject failure to make progress on reduction of emissions to date. There's a recognition that what we actually need to support decarbonization, but in a way that enables continued operation of the global economy without emissions, we need to substitute energy services currently being provided by fossil fuels. And nuclear energy is a really interesting option to do that because it has a tiny environmental footprint, it has a very high capacity factor, which means it operates at 90% of the time, and it can produce not only power but also heat without emissions. And we'll hear in a moment, I'm sure, from my dear colleague, about a very pioneering project to provide heat and power to an existing industrial energy user. But through TerraPraxis, what we've been seeing is really an astonishing level of interest from large industrial energy users, global technology companies, oil and gas companies, steel, chemicals, and in the marine sector, that are at the point now in their investment cycle where they're looking at how they're going to meet their 2030 targets. And every single one of them are looking at nuclear energy to support their decarbonization goals, but in a way that meets their business drivers. So matching the cost and performance that's currently provided by fossil fuels with new emissions-free energy services from nuclear technologies. Now, we have a long way to go for the nuclear industry to actually respond to that demand in a meaningful way, but we're working on strategies to achieve that. So we have this interesting opportunity right now to really accelerate the commercialization of nuclear technologies, and we can learn a lot from the success that we've seen in the renewables space, which enjoyed, very strong support and advocacy from policymakers, from the environmental community, from leaders like yourselves that understood the potential to change the delivery of solar and wind from being something that was expensive and slow and vertically integrated and frankly niche into something which could be really commodified as a highly competitive, scalable and transformative solution for our energy and decarbonization needs. Let's apply that same successful strategies to the acceleration of commercialization of nuclear.
Thank you. Another thing that we keep on mind, and we were chatting, and I was saying that when looking into the energy segments, we go onto solar, to wind, to fossil fuels, and then when taking in consideration nuclear, one other thing that gets to us is within the development is that the time that it takes to be constructed and then the costs. It starts at one cost, and the sensation we have from a Brazilian perspective, we are still with our Angra 3 to be built, and it goes on and it goes on, and it hasn't finished yet. So I will start with asking to you, Cosmin, and then asking for some complementation from Cam, if you could share a bit on this time and this budget. How is it been changing over time? Can we expect it to be in the lower time to
Sure.
budget?
Let me start with drawing a parallel. Right now we're talking about two types of nuclear. Traditional nuclear that has basically, it's probably 70% construction and maintenance. And each particular step of it is fully regulated and observed by the regulator. If I were to draw a parallel, think about going to one of those old school English style tailors that look at every part of your body to try to fit that particular suit for you, and it takes time. And it takes rework, and you cannot make sure that you have it available that particular day. However, we have fast fashion that's coming out now. And you have very good suits that are being produced at very good quality, but they're in series. Now, if I were to draw a parallel, the SMRs will probably be the fast fashion of nuclear, in the sense that 80 to 90% of them will be pre-constructed. And this is due to advancements in manufacturing and manufacturing techniques, because now you can do military grade, you can do nuclear grade components that will be prefabricated and assembled on site. Now, this obviously imposes a huge challenge to regulators, as they will need to look at how do they work with supply chains, which become the most important aspect of the development, to be able to make sure that all of these particular quality assurance manuals and so on are at par, and they're okay with it. From my perspective, I think that the average construction time period of an SMR can be half of that of a regular reactor. So moving from 6 to 7 years to probably 3.5 to 4. The licensing, now this is where it's going to take a little bit of time for the first of a kinds, as you tailor the design to a grid need. But then if you keep the design the same, you automatically replicate it, and it becomes a very smooth and easy to permit process. And as you can see, even in the EU, if we're looking at the Net Zero Industry Act and the recent evolutions of that, we are setting ourselves up for success through an accelerated permitted system. So the real benefits will be the fleet deployment. And at that point, you enhance supply chains. Now, if I'm to draw a parallel with a similar revolution that happened probably 12 years ago in the solar and renewable industry, we can see the first panels and solar and renewable installations of being a little bit high in terms of cost per megawatt. If I remember correctly, around 2012, a solar panel, a solar farm was trading around in Romania at least, around around 6 million euros per megawatt installed, and now it's below $1 million. How did it happen? Well, it took 12 years of deployment of scale and public funding to accelerate the development of supply chain and lower the costs of that particular technology. The same thing will need to happen with nuclear. And actually with all technologies, to be honest, if we want to achieve full decarbonization. And I'm not sure we've seen all the technologies yet that are needed, and we're not talking about them, that are needed to achieve full decarbonization. So here is where we're going to have public-private partnerships that will have to move forward. And it's a new development model. And this is one of the points where governments, regulators, for example, can work with certification organizations to develop, to achieve that. You're going to have reactor vendors and designers that will be working with construction companies and private funds together with government to try to accelerate deployment. So there are a number of lessons to be learned, and there's a change from the fully, how do I call it, sovereign model, which has been the norm in nuclear. And it's an interesting and transformative change, but that also requires a lot of understanding and openness and trust building. So it's an exercise that at the end of the day will help reform societies, but build trust and bridges, not only between countries. We're seeing most of these being multinational efforts, but within country, between various sectors that will be there. So at the end of the day, it's a new philosophy with a topic that's been highly sensitive. It hasn't been discussed very much in the public openness, and it will require a lot of reform for itself. But I think that we have good practices in other areas that can be easily replicated, and we can achieve that.
Thank you very much. And with that, I'll pass to Mr. Cam. I think we could go a bit a step back in terms, I don't know if all the audience, and I'm still a learner, I would love to understand, when we're talking about the small modular reactors, and we do need more knowledge within, broad knowledge in terms of it, regulation support and policies. Could you bring us a bit, so on the regulation side, on the policies, and about it, and how this technology can really reframe now the energy transition in terms of new energies being built?
Sure, thank you so much. Yeah, so if I just go back a little bit and sort of zoom out for a second and look at the problem that our planet is facing, our world is facing. There's a huge need for carbon reduction. I mean, we know that, where if we don't do that, I think our civilization is doomed. We got to make that happen. At the same time, the energy need is increasing. So you got two forces, right, that work in the opposite direction. And the energy need that is increasing dramatically around the world. Population growth, also the energy need per capita, the industrial requirement for energy, all of that is increasing. And one of the things that's happened recently, maybe, and especially within the last year, is the energy need of AI and data centers. I mean, that has completely changed the game. I mean, the amount of power these data centers need. I mean, I was just talking to a hyperscaler recently at their conference, and they're going to need like 10 gigawatt of power by 2030. And, so all the energy formulas that we've been thinking about, we got to throw out of the door and sort of say, how are we going to meet the energy need? So when you sort of look at it and you say, okay, then if we're not going to use the fossil fuel, of course we need renewables, but how are we going to solve the problem? Then you come to this solution that, okay, nuclear. Now, if you come to sort of solution of nuclear, then you talked about the perceptions, right, of nuclear and all of that. That's why X-Energy was formed in 2009. I mean, I'm personally a space cadet. My companies are in space. But I did this because I wanted to really combine altruism with capitalism, make a difference, right? And so this is the reason for what I call the Generation 4 nuclear reactors, right? The founding principles that I came up with for X-Energy were 4: clean, safe, secure, affordable. energy solution that's 100% clean. And as the gentleman indicated, my first idea was hydrogen. And I realized that the hydrogen economy is not viable without a heating source that make it economically viable. And that's how I turned into nuclear. And so also it has to be, so the generation 4 nuclear reactors, X-energy, XC100, is 100% safe. And when I say safe, I don't mean by some electronic intervention that, if you lose cooling, then, you get supercritical like it happened in Chernobyl or Fukushima. No matter what happens, they're intrinsically safe. That's the XC100 reactors. Doesn't matter if there's an earthquake or if there's a tsunami, so that's why I think the perception is changing. And also secure, so that it cannot be.
I think that it's interesting for the audience to know, when you mean safe, because what happens, tell me if it's that. We had the enrichment of the uranium, it goes on happening. But now when you're talking about these new technologies, if something happens and it goes out of control, it stops the enrichment.
Not the enrichment. What happened is actually the feedstock to our fuel is high SALEU, the enrichment that's up to 20%. That goes inside the fuel. And so if, let's say, you lose cooling, and by the way, this all 100% been tested. So what I'm saying is not just the hypothesis, it has been tested, 100% proven. So if you lose cooling, like what happened, let's say, in Fukushima, the temperatures goes up a little bit, and then it automatically comes down, so that it would never go to a supercritical situation where you have radiation leak and dangers. So that's why it's 100% intrinsically safe. And the physics is not by electronics, it's by physics itself. That's why this is fundamental. Holy grail in nuclear is safety, and we've solved that problem. 100% proven, de-risked, and today, actually, Chinese are operating a pebble bed modular reactor, generation 4, even though it's not a small modular reactor, is high. That sort of proves that this technology actually de-risked and it actually works. And then the last piece is something that is affordable, right? So you can compete with natural gas. And we're really fortunate that we have created this partnership with the US government. So US government is actually in a private-public partnership, is our partner. We are very fortunate to win a $2.5 billion grant. It's a 50-50 cost share with US government. And now we got a customer we're very proud to have Dow Chemical as our first customer. We're building the first plant in Seadrift, Texas. So you have this partnership that I think you discussed, where you have the US government, you have a technology provider, a vendor like X-energy, and working with a customer. And actually, this is interesting, 25% of the world energy today is industrial needs, right? And what HTGR, the technologies like X-energy provides, is because of the high temperature they generate, is really perfect for hydrogen production, for water desalinization, for cement factories, for petrochemical companies, as well as he indicated, what we actually do is it doesn't require water for cooling. The modules can be carried in the back of a truck, back of a train, and you can deploy it anywhere. You can literally have one of our SMRs in the middle of a data center or in the middle of a city, and doesn't require as much footprint to be able to do that. And then one last item that I want to say is, because of the need of amount of power that the world needs, we need to completely think differently. We can no longer go with sort of one-off scenario. We need to be able to scale this like you create cars. So our idea is we will have factories where you sort of create the modules like Legos. You take it to the site and you assemble it, and you have fuel factories around the globe that actually feed the reactors.
Thank you very much. Mr. Miyanaga, I was listening to you in the room as well and want something interesting from Mitsubishi's perspective. So when moving forward, we started saying in Japan, in the US, but definitely for the developing countries, this can also be an interesting alternative. And if we really move forward and with the right policy in place and competitive price, this could be something interesting. If you could explore a bit of this in terms of how could, with the right price, being competitive, how could it help and for which uses?
Yes.
That's the thought.
I think the small modular reactor, yes, for example, it is a very, a kind of a breakthrough technology for the near future because of with such kind of concept, the modular design is a very the standard, and also small means small modular means that I think as you have said, the prefabrication at the factory as much as possible, and then the cost and the quality will become much more reliable, and then the easy to manufacture or produce. But I think for the very gigantic the conventional reactor of we have established expertise and skill, but we need to maintain a very high quality engineering level and workmanship and so on. But I think it is necessary for the future development too, like the nuclear fusion and others. That kind of large scale reactor will remain as a very important facility. But I think for other common the popular use, maybe there will be some near in the future. I think prefabrication as much as possible, and that means the site work will be reduced very much. And not only the quantity of the volume of the site work is reduced, the difficulty is again, because very high-rising and big heavy machinery installation requires a lot of difficult foundations and the installation techniques. But the distributed, small, a little bit compact design, small modular reactor will ease a lot of site work. That is not only the cost of the labor, but also time duration will become, and we can expect that kind of the benefits. And the capital expenditure will be reduced. And I think with the common design, I think that we can expect another, cost reduction. So, and looking at the current situation and the energy cost, with the renewables, when we look at the capital expenditure, of course, compared to the wind turbine, onshore wind turbine, of course, the nuclear is much more expensive. But I think it lasts much longer. And also the offshore wind farm is more expensive. And then if we use such electricity to produce hydrogen for some purposes, and then I think such kind of total energy cost and T&D, transmission and distribution network cost will require. So I think as a whole, the energy cost is rising, and looking at such kind of the current situation and the future costs and the price situation by other renewables and other sources, the nuclear competitiveness will not be deteriorate. I think probably I can expect we can make it more competitive in terms of the cost, and also in terms of the construction cost and the capital expenditure cost. And the further to say, the fuel itself, because if we enrich a little more, and we can expect a longer continuous operation, and in the future, by doing so, the operation will become very stable, and the cost expectancy will not be, we cannot be concerned about the future oil and gas or the other kind of the demand and supply. Yes, energy cost, or the operational, the fuel cost, and other kind of concerns. So I think the new nuclear will provide us a very good opportunity to be a basic, very reliable, stable energy source.
Thank you. With that, Christy, thinking of all these things that are going on, if you had to line up here, top challenges, risks being evaluated, how could we, looking at where we are now, to bring this alive in terms of being something feasible and achievable for many countries? What are the main challenges and risks?
So obviously the technology readiness is absolutely key, and we've heard about the importance of technology demonstration, and that's underway now. I mean, we have many demonstration projects underway, including X-Energy, and also including some of the micro-reactors, which are very interesting. Those are the reactors that can be made in factories today, mass-produced at scale, licensed in the factory. And we'll see demonstrations of those technologies starting to operate as soon as 2026. So that really is a time frame that could be relevant to the 2030 targets that we were talking about a moment ago. But in addition to that, to achieve the speed to market, to achieve the scale of deployment that's needed, to achieve the cost and the performance requirements that are going to be needed to meet the industrial energy users' requirements, we're going to need to see significant investments in standing up supply chains. Now, organizations like MHI, as well as other large manufacturing companies that are already building high quality, high performance, highly regulated infrastructure, could absolutely be building infrastructure for nuclear technologies as well. So this isn't all starting from new. It's really about transferring existing industrial capabilities to meet this need. In addition, we'll need a licensing pathway that's really commercially viable. And we've been working with a group of oil and gas companies in the United States interested in deploying microreactors to support decarbonization of their upstream operations. We identified 50 gigawatts of existing generating assets of between 1 to 5 megawatts, so tiny, 50 gigawatts of existing generating assets that they're interested in decarbonizing with microreactors. So we took that to the regulator in the United States, and we're feeling cautiously optimistic that it would be achievable to develop a commercially viable licensing pathway to enable the decarbonization of those assets through a commercially viable licensing pathway that would enable rapid delivery from decision to generating asset. So licensing is really key, but there's ways in which it's not just sort of regulatory reform and the regulators coming to the table, which is really critical. It's also designing out regulatory scope. It's also about reducing as much as possible the nuclear island. We're seeing examples of separation of the nuclear heat island from the power island, which just overall reduces the regulatory scope, the regulatory oversight needed, all the way through from design engineering to manufacturing or construction, and then operation. There's also licensing innovations or design innovations that can enable standardization, which means that you might license once, but then be able to build many, many, many. And then we're going to need to see collaboration internationally between regulators to enable, proven, demonstrated technologies to be deployed into multiple markets.
Who are the companies that you think that would be the first adopters, the segments that would be the first adopters within this?
So Microsoft published a policy briefing at COP28, recognizing the role of nuclear energy alongside renewables to support the decarbonization of their operations, and they're interested in accelerating the commercialization of nuclear technologies through, direct investments, signing PPAs, policy advocacy, So certainly the data center sector that has tens of gigawatts of demand in the 2030 timeframe and needs highly reliable, emissions-free energy. I mean, 99.999% at the gigawatt scale. But then also oil and gas is really interested in decarbonizing oil production to enable continued access to resources in future, continued license to operate. And then we're seeing the marine sector as well. The IMO finally last year set targets for 2050 decarbonization with gates along the way starting in 2030. And the marine sector is also very interested in accessing energy services from nuclear energy.
Thank you. Cosmin, one part that we haven't tackled yet, and this is a perception, but I think it's been changing as well, is relative to the waste. So we've mentioned here the scaling up, the investment needed to scale this up, the regulation, that these are small reactors, so it's a lot safer. But then with the waste, what could you bring to us in terms of?
Let me start with the first thing. The waste produced by nuclear energy in terms of footprint per megawatt produced, it's the smallest amount of waste out of all energy production forms. And I've had the opportunity in my brief career to see multiple forms of electricity production. Supplementary to that, it's probably one of the most regulated industries in terms of management of waste. So currently, I would say that this is probably one of the safest areas to look at. However, and this would be the point that I'd like to put into, is that with less production and the newer technologies that we're seeing have a probability of smaller waste footprint, but we're looking at advanced reactors as well. So right after these SMRs that we're talking about that are using conventional technology scaled down the size, we are looking at advanced reactors that could potentially be waste burners, or we can see reprocessing of nuclear waste to be able to have closed-end cycles. And a lot of the advanced Generation 4 technologies that will be the next step afterwards are looking at that. So in Europe, at least, a lot of the countries are looking at treating waste as a resource. So I know there's a debate around proliferation in other places, but with the advancements in technologies that we're seeing today, a lot of the old of the concerns around recycling are going away because there's more and more solutions that are coming out there that are proliferation proof and also help you achieve more energy production without necessarily having a waste footprint. So at the end of the day, when you're going to have an energy system mapped out, probably by 2050, as everyone's planning, there's a goal by 2032, 2035, and one by 2050. When you look in the long term, you will see mixed technologies that will help complement and close the fuel cycle. And in that sense, you can actually have zero, if not close to zero, if not zero, footprint. So the idea is when you're going to start looking at deploying these type of technologies, the outlook needs to be very, very long. I know that the outlook that we're looking at right now has to do with the repayment of the financial structures that are being put in, which is probably 15 to 20 years after commissioning of a nuclear facility. But a nuclear facility operates can go all the way up to 80 years.
Wow.
So the commitment is a century-long commitment. Therefore, the view and the plan that everybody needs to implement is a 100-year plan. And that's basically probably the number one piece and step that every government or entity that wants to get into this or region has to look at a 100-year plan. And, yeah.
That will hopefully change, right? When we have a situation where we have manufactured reactors being made at scale, it's all about de-risking investment and not necessarily requiring that very, very long payback time. Really, the fundamental de-risking that's needed is around confidence for budget and schedule and ultimately cost. And once we achieve those very low costs and that confidence around budget and schedule, then there's going to be a massive investment opportunity that doesn't necessarily rely even on those very long operating lives.
Yeah, but you want to depreciate your technology as much as possible. So
as soon as possible.
Yeah. So if you want to have true gains, probably with CapEx being the highest cost line in the cost structure of a particular nuclear reactor and the resulted levelized cost of electricity, once you've depreciated it, how do you say, what you have afterwards is gravy. So having a long-term use case makes a lot of sense.
Do you, Mr. Ken, want to add up to this?
Yeah, I mean, like in our case, I agree with her that I think we need different kind of thinking. To be honest, if you sort of look at X-energy, in many ways, we sort of follow the SpaceX model, that we want it to be very expansive, disruptive in terms of technology, and find a different way where we can solve this problem. So not only we want it to be disruptive from technology perspective, also from our business model perspective. So finding a government partner that helps you with your first-of-a-kind cost. I mean, just think about it. If somebody came and said, hey, I'm going to give you $2 billion, and I don't require any IP, and you get no dilution, that's a pretty good deal, right? And also providing maybe additional tax credit, like in the United States with the Inflation Reduction Act. I mean, that's really helped us a great deal. We feel like we're going to be extremely profitable business in a very short period. Once we get past our first of a kind, which we're very close to do that. And by the way, the other thing we're doing is we're probably, I think, maybe the only company in the world that not only producing nuclear reactors and microreactors, we also provide fuel for the nuclear reactors. So like as he indicated, a life of a nuclear reactor is 60 to 80 years. So think of it like selling printer cartridges. So I think fuel business by itself could be extremely profitable as well. And let me just share this, which I think is really important. As I started in 2009, the company, creating a nuclear business and a commercial front is not easy. Let's just put that out there. Since I'm in space, I tell people that it's easier to land a rover on Mars than really start a nuclear plant and build it from scratch. And the reason is, I think there are three bubbles that need to work together very closely and integrated, and if they're not, it's not going to work. So first is the technology. You got to have the right technological solution, otherwise it's not going to work. I think the second bubble is regulatory, right? So if you design the most elegant reactor ever, and you can get it licensed, you haven't accomplished anything. Now, let's say that you have now come up with an incredible design, and you can get it licensed, but it's not economically viable in terms of kilowatt per hour. People are not going to use it, right? As much as we have this need for decarbonization. So economic viability, the regulatory, and technology, I think that all needs to be working together to make this happen. And I think that requires, I believe, different kind of thinking rather than traditional nuclears, where it takes long time to produce. And I think one of the key things is standardization, because you don't want to go back to the regulator every time you put a new one in. So the way we're doing ours, we have a 4-pack that is standardized. We're going to get licensed for this. And every time we sell it, that's what we're going to sell. Like a box that has been already licensed, so we can repeat it over and over and over again.
Thank you so much. We are in like 50 minutes to end. I think that we've got a very interesting perspective here in terms of it's much safer than what we had the perception before. Technology is already there. We still need to speed it up, and for that we will need economical viability. And to achieve this economical viability, we need some support. We need some schemes in the beginning, but then bringing it along, we will have like long-term cycles, reliable energy, And that will be able to be used not only by developed countries, but developing countries and for several uses, industrial uses, data centers. So with that, I think we are ending up, but I'd very much like to thank you panelists for this and for the audience for being here with us today. Thank you.